Black holes, those enigmatic cosmic objects where gravity reigns supreme, were once thought to be inescapable abysses. Nothing, not even light, could escape their gravitational pull. However, in 1974, renowned physicist Stephen Hawking proposed a revolutionary theory that shook the foundations of astrophysics. Black holes could actually emit radiation and slowly evaporate over time. This phenomenon, known as Hawking radiation, arises from the bizarre world of quantum mechanics, where particles can pop in and out of existence. Imagine a vast, empty space, the vacuum of space itself. According to quantum mechanics, this emptiness is not truly empty, but teeming with virtual particles, constantly appearing and disappearing in pairs. These particles, born from quantum fluctuations, exist for a fleeting moment before annihilating each other, returning to the void from whence they came. Hawking realized that something extraordinary happens when these quantum fluctuations occur near the event horizon of a black hole, the point of no return. The intense gravity of the black hole can warp space-time so dramatically that it can separate these virtual particle pairs, preventing them from annihilating each other. Picture a pair of virtual particles popping into existence just outside the event horizon. One particle, by chance, appears slightly closer to the black hole than its partner. The immense gravity of the black hole can capture this unlucky particle, dragging it across the event horizon, never to be seen again. The other particle, however, finds itself on the precipice of the abyss, just far enough away to escape the black hole's clutches. With its partner trapped inside, this particle is no longer bound to annihilate and can escape into the vastness of space. To a distant observer, it would appear as if the black hole itself is emitting particles, radiating energy into space. The escape of Hawking radiation from the gravitational pull of a black hole seems counterintuitive. After all, nothing, not even light, can escape once it crosses the event horizon. However, the key to understanding this phenomenon lies in the nature of virtual particles and the warped space-time around a black hole. Virtual particles are not like ordinary particles. They exist in a sort of quantum limbo, borrowing energy from the vacuum itself. When a virtual particle pair appears near the event horizon, one particle can gain enough energy from the black hole's gravitational field to become a real particle, while the other particle carries negative energy. This negative energy particle is crucial because it effectively reduces the total energy of the black hole when it falls in. Remember that energy and mass are equivalent, as described by Einstein's famous equation E equals mc squared. So as the black hole loses energy, it also loses mass. Section 4. The slow fade of black holes. The rate at which a black hole loses mass through Hawking radiation is inversely proportional to its size. This means that smaller black holes evaporate much faster than their larger counterparts. In fact, microscopic black holes, if they exist, would evaporate almost instantaneously in a burst of energy. For stellar mass black holes, those formed from the collapse of massive stars, the evaporation process is incredibly slow. The temperature of Hawking radiation is inversely proportional to the black hole's mass. So these black holes are incredibly cold, radiating energy at a snail's pace. It would take an unimaginable amount of time, far longer than the current age of the universe, for a stellar mass black hole to evaporate completely. Supermassive black holes, the behemoths lurking at the centers of galaxies, have even lower Hawking temperatures and evaporate at an even slower rate. These cosmic giants will likely continue to grow for billions of years, consuming stars and gas clouds before eventually fading away through Hawking radiation in the distant future. Section 5. Properties of Hawking radiation. Hawking radiation has several remarkable properties. First, it is a thermal spectrum, meaning that it consists of a range of particles with different energies, similar to the radiation emitted by a hot object. The temperature of this radiation is inversely proportional to the black hole's mass, so smaller black holes are hotter and emit radiation at a higher rate. Second, Hawking radiation is theoretically predicted to be incredibly faint, making it extremely challenging to detect directly. The faintness arises from the low temperature of black holes, especially for stellar mass and supermassive ones. Despite its faintness, Hawking radiation has profound implications for our understanding of black holes and the universe. It suggests that black holes are not eternal prisons, but rather dynamic objects that slowly evaporate over time, releasing their captured information back into the cosmos.
Like and subscribe to start your journey today.